Hey everyone, welcome back. I hope you're well. And in this video, we're going to take a look at conditional probability. So specifically what we're going to do is we're going to take a brief look at formal conditional probability, and then we'll dive into informal conditional probability, which is where we look at conditioning on tables. But without further ado, let's get into it. So let's start with our introduction. So conditional probability is just the likelihood that an event occurs based on the occurrence of a prior event, right? So it's like the probability that, I don't know, if you're rolling dice, that you get a 6, given that you rolled a 6 before, for example, right? So if you have two events, let's call them A and B, then we're able to condition on one another, right? So what that condition word means is that we can essentially look at, like, it's almost like a filter. You can feel like it's a filter, right? So we're filtering on A based on B, or we're filtering on B based on A. So for example, this means that we can find the probability of A if B has already occurred. So the probability here, so this is the formula for conditional probability, which we're not going to derive at all or anything like that. We're just going to look at how we can apply it. So here it is. It's the probability that A is given B. So this sign here means given. So the probability of A given B is the same as the probability of A and B occurring divided by the probability of B. Similarly, we can find the probability of B given that A has already occurred. So it's just almost the reverse, right? So the probability of B given A is the same as the probability of B and A occurring divided by the probability of event A occurring. Now, note that independent events are unaffected by prior events, right? So conditioning on a independent event won't actually affect its outcome. But if we condition on a dependent event, right, then that is going to be affected by prior events. All right. So as an exercise, we've got these formulas here. What we'll do is we'll rearrange them for event B and for event A. For example, so in our first case, if we had the probability of A given B is equal to the probability of A and B occurring divided by the probability of B, and we want to rearrange for the probability of B, first thing we're going to do is multiply both sides by the probability of B, because this is the denominator, right? So if we multiply both sides by the probability of B, we're going to get the probability of B multiplied by the probability of A given B is equal to the probability of A and B, and the probabilities of B will cancel out like so, right? So that's your level 1 algebra. So now we just want to get rid of this A given B here on the left side. So how do we do that? Well, we have to do the opposite, operation, which is division in this case. So next we're going to do the probability of B is equal to the probability of A and B divided by the probability of A given B. And this is our rearranged formula. Now, I guess as well we could do find the probability of getting the intersect. So how do we do that? Well, and I'll highlight this one here as well. So it's just one step here to get rid of, to find the probability of A intersect B, or the probability of A and B occurring. We just have to get rid of this probability of B. So how do we do that? Well, we do the opposite operation, which is multiplication in this case. So we're going to get the probability of A given B multiplied by the probability of B is equal to the probability of A and B. And now we've rearranged for the probability of A and B. So this is our final answer. And we've actually already done it down here, so that was kind of unnecessary. Okay, so let's look at some problems. So let's solve this first problem. So you're drawing from a standard deck of playing cards. Find the probability that, given you've already drawn 3 red cards in a row, the next card you draw is also red. So what events do we have here? So we got event. Let's call event A the event that I guess we've already drawn 3 red cards. So the event of drawing 3 red cards, right? So that's one event. And then let's look at our second event. Well, the second event has to be this one here, which is event B, we'll call it. And we'll say that this is the event that the next card we draw is red. So this is the event of drawing a red card. So what do we want to do? So we want the probability that given you have drawn 3 red cards in a row, the next card you draw is also red. So the first thing we look at is what is the given event, right? So we always say given some event. So we're looking for that keyword given, or sometimes it might be if. So given you have drawn 3 red cards in a row. So that's going to be the probability of something given that we've done the 3 red card draw, which is event A. So what's the other event left over? It's event B. So what we're saying is that if I've already drawn 3 red cards, the next card is going to be red. So that's event B. So we want the probability of B given A, and we know from our probability formula that this is the same as B intersect A divided by the probability of A. Okay, so now we can look at actually calculating this probability. So first thing we need to know is the probability of B intersect A. Now, what's this probability? Well, it's the probability of first drawing a red, so the event of drawing 3 red cards and then drawing another red card, that's the event of drawing 4 red cards. So the probability of drawing 4 red cards is the same as, well, we start with, I think 26 over 52 red cards. Then we go down one, right? So we've already drawn, we don't replace the cards into our deck, right? So there's only going to be 25 red cards left out of 51. Then there's going to be 24 red cards out of 50. And then finally, there's going to be 23 red cards out of 49, right? So that's 4 cards drawn, and all of them in consecutiveness are all red. Now, let's look at the probability of A occurring. Now, what's the probability of A, the event of drawing 3 red cards? Well, this is pretty trivial to calculate. It's almost the same thing as before. It's going to be the first red card being 26 over 52 multiplied by 25 over 51 multiplied by 24 over 50. And here we've actually drawn all 3 cards, and we're assuming that they're all red, and so we'll stop there. So, yeah, if we want to now calculate this probability here, this is the probability of B given A, which is equal to the probability of B in A, which is 26 over 52 multiplied by 25 over 51 multiplied by 24 over 50 multiplied by 23 over 49, all over the denominator, which, and to save time, I'm going to just duplicate it and put it here. So normally we'd put in the calculator and then solve it to find the answer. But in this case, we can do some quick manipulation, because we can actually see that, well, this term's going to cancel here, this term's going to cancel here, this term's going to cancel here. And so the probability of B given A is 23 over 49. That is to say, given that I've already drawn 3 red cards, what's the probability of drawing another red card? It's going to be 23 over 49. And that does logically make sense, right? All right, let's look at my second question here. So as an avid lover of Macca's, you're eager to maximize your winnings in this year's edition of Macca's Monopoly. You only care about the instant win food prizes, and in particular, you only want to win Big Macs, McChickens, and Sundays. Now, the probability of getting an instant win is approximately 0.132. So given that you have an instant win, the probability of getting a Big Mac is approximately 0.1. The probability of getting a McChicken is approximately 0.15, and the probability of getting a Sunday is approximately 0.3. So part 1, let's find the probability of winning an instant win, and the prize awarded was a Big Mac. So if we think about what probability we're trying to find here, we see that there's an and here. So I guess let's define our events. So let's let event A be the event of winning an instant win. In fact, let's actually rename it I, because I is a better representation for instant, right? And then let's let event, let's call it event B, be the event of, I guess, winning a Big Mac. And let's let event M and S be M for McChicken and S for Sunday. Right, so we've made our definitions. So we want to find the probability of getting an instant win and winning a Big Mac. So that's going to be the probability of I and B. So how do we work this out? Well, if we've got conditional probabilities, we're going to want to rearrange our conditional probability formula. So if you remember, if we have the probability of A given B, it's the same as the probability of A and B over the probability of B. We're wanting to rearrange for this part here, and so if you revisit what I did at the start, this is the same as the probability of A and B is given as the probability of A given B multiplied by the probability of B. So if we apply the same concept here, the probability of I intersect B is the same as the probability of I given B multiplied by the probability of B. Okay, so so here's the thing. What do we have here? We've got the probability that given you've got an instant win, getting a Big Mac is approximately 0.1. So what's this saying? It's saying that given we have an instant win, the probability of getting a Big Mac is 0.1. So the probability of getting a Big Mac is the event B. So we've got B given I, but here we've said it's the probability of I given B. So we're kind of stuck here, right? So here's a pretty cool trick that's good to know. The intersect of I and B is the same as the probability of B intersect I. So now what we can do is rearrange this. So this is the same as the probability of B given I multiplied by the probability of I. And now we're good to go, right? So these two are equivalent. So the probability of B intersect I is going to be equal to the probability of B given I, which is this probability here, right? Which because given that we've got an instant win, the probability of getting a Big Mac is 0.1. So this is the same as 0.1 multiplied by the probability of getting an instant win, which is 0.132. So 0.132. So if we multiply these up, we get 0.1 times 0.132, which is the same as 0.0132. So it's not very likely, right? It's not looking very good. That's only like, what, 1.32%. So let's do part 2 now. So let's say this is part I. Let's do part I. So what's the probability of getting an instant win, and it was a Sunday? So this is the probability of Sunday intersect instant win, which is the same as the probability of Sunday given instant win multiplied by the probability of getting an instant win. So it's the same as essentially in part I. So the probability of getting a Sunday given that you had an instant win is 0.3 from this line here. This is multiplied by 0.132 as before, and our probability is therefore 0.3 times 0.132, 0.0396. Okay, and so if we look at finally at part 3, we're going to find the probability of getting an instant win and being disappointed. So what is this? How do we work this out? So what's the probability of being disappointed? So if you remember here, we only want Big Macs, McChickens, and Sundays. So essentially, if we get the union of getting a Big Mac, a McChicken, and a Sunday, and then subtracting one from that, we'll be able to get the probability of getting something else, which is not what we want, and then we're going to definitely be disappointed in that case. All right, so how do we do that? So essentially, we want the probability of getting, let's say, what letter should we use? Well, we use letter N for no good. Intersect instant win is equal to the probability of no good given that you get an instant win multiplied by the probability of getting an instant win. So what's the probability of no good given an instant win? Well, it's going to be 1 minus the sum of these probabilities, right? So it's going to be 1 minus 0.3 minus 0.15 minus 0.1, which is equal to 1 minus 0.3 minus 0.15 minus 0.1. That's 0.45, right? And that kind of makes sense, right? If you think about it, right? Given that you got an instant win, if you don't get a Big Mac, a McChicken, or a sundae, or the rest of the probabilities has to be something to 1, right? So if we subtract all those out, we're going to get something else with the probability of 0.45, right? So with a probability of 0.55, we do get something that we want. Anyway, so we've got the probability of n given I. So this is going to be the same as 0.45 multiplied by the instant win probability, which is 0.132. So if we multiply these together, 0.45 times 0.132, we get 0.0594. So the probability of getting an instant win and being disappointed is about 5.94, or about 6%. All right, let's now look at informal conditional probability. So if the last section, if it kind of went a bit over your head, I wouldn't worry about it too much. This section is a lot easier, and this is the main thing that we want to focus on. So what's informal conditional probability? Essentially, if data is presented in a table, we can actually calculate the conditional probabilities without requiring the knowledge of the above formulas. So here I've given you an example where we've got male and females, and the other part of the table, or the columns of our table, are Apple and Samsung. So if the person prefers Apple products or if they prefer Samsung products. So how do we actually condition on a table? So first, we need to identify the row or the column, which is the condition, right? And then once we've done that, we just calculate the probability of the event occurring from that conditioned row or column. So what do I mean by that? Well, let's take a look at an example. So it's a lot easier than it sounds. So first of all, what is the probability that a randomly selected person prefers Apple products given that they are male? So as we did before, the first thing we need to do is look for that given part of the statement, or look for the keyword if. So our keywords are given or if, right? Or even where probably is conditional as well. So if we look at our statement here, we've got given that they are male. So what that suggests is that we are conditioning based on if they are male. So we're going to look for the male row in our table. And as you can see, I've already highlighted it here. But yeah, so the first thing we do is we identify which row that is. The next thing that, so we can actually go ahead and solve this probability now. So we know that we're only looking at this highlighted row here. So what's the probability that they prefer Apple products from this row? Well, it's 5, right? So it's 5 out of the total, which is 11. So 5 out of 11, which is equal to 0.455. So, and let's look at our second example now. What's the probability that a randomly selected person is female given that they prefer Samsung products? So first, let's look for that conditional keyword. So it's given in this case. So given that they prefer Samsung products means that we're conditioning based on the Samsung column. So that's this column up here. So maybe I'll highlight it like this. So now we can actually go ahead and solve the question. So what's the probability that a randomly selected person is female from this specific column? Well, it's 9 out of the total, which is 15, because 15 is highlighted, right? So we don't consider anything else which is not highlighted. All right, so 9 out of 15 is equal to 9 divided by 15, which is 0.6. All right, so now that we've looked at some of the fundamentals around conditional probability, we can actually go ahead and complete one of the questions from the probability standard. So let's go ahead and do that. This paper's from 2020. So essentially what they've done here is they've done a survey in North America around EV ownership and if they have a home solar system. So part AI, what proportion of survey respondents owned an EV or a PHEV? So the first thing we want to do is we want to consider, is this a conditional probability? So in order to determine that, we need to know, or we need to identify if there is a conditional keyword. So is there an if, is there a given, or is there an where? The answer is no, right? We have an or. We have an or. So or is actually the word for union. But if you don't know what a union is, it's essentially where we're going to add up two kind of different probabilities. Or two different maybe elements. We'll go with that. So how do we do this? So what proportion of survey respondents? This tells us that we're looking at the total amount of people, right? So what's the total amount of people? It's 2,000, right? So out of 2,000 people, what's the probability that they owned an EV or a PHEV? So essentially what we're going to do is we're going to consider the EV part first. So we look at the EV row, right? So we're going to be looking down this row. And we also want to know the total, right? Because we're looking at the total number of people that owned an EV. So what we do is we go down here, we go down the row, and we also go down the total column, and we look for where the row and the column are going to intersect, or our arrows are going to intersect. And they intersect at this entry here, right? Which is 275. That kind of makes sense, right? So what about a PHEV? So in this case, get rid of my arrows. What's the PHEV row? It's the second row. So we're going to go down the row and we're going to be looking for the total amount because we're looking at the total amount of people that own a PHEV. So we're going to go down the column here and look where they intersect, and that's actually at this entry here. So that's going to be plus 145. So now if we actually do the probability, 275 plus 145 divided by 2000, that gives us 0.21. Part I, which type of vehicle owner in North America is more likely to have a home solar system according to these survey results? So there's a few different ways that you can think about this. I'm going to say, in this instance, let's think of it as a conditional probability, even though it doesn't really have a conditional keyword. So what I mean by that, essentially, we want to know if they have a home solar system. Given that this is the table, we want to use our conditional probability techniques, right? So essentially, if we know what type of vehicle they have, we can condition on that and find out if they have a home solar system. So essentially what I'm saying here is the probability of having some kind of vehicle the probability of having a home solar system given that they have some vehicle. So that's what we're actually interested in here, right? Because that's going to tell us which type of vehicle owner is more likely to have it, right? The bigger the probability, that's going to tell us, it's going to tell us which vehicle is more likely, right? So we're going to have to do this 3 times. So let's do the probability of having a home solar system given that you drive an EV. This is equal to the probability. So what's our condition here? Or where's our given? So given that we have an EV, which means that we're going to look at our EV row, which is this row here. What's the probability of having a home solar system? Well, we're looking at a home solar system, which is this entry here, and we just look at the total, which is highlighted in red. So that's 104 out of 275. What's the probability of having a home solar system given that you have a PHEV? Well, we're going to do the exact same thing as we've done before. So we're conditioning, our given condition is having a PHEV. So we look for that row, PHEV, and we highlight it. we also want to know from this row who has a home solar system. That's going to be this same column here. So it's 45 out of 145. So what we're saying here is 45 out of the 145 PHEV owners have a home solar system. And finally, the probability of having a home solar system if you have a non-electric vehicle is essentially 205 over 1580. So because the denominators are different, we need to actually hand calculate them to find the largest probability, which is 0.378 here. 45 divided by 145 is 0.310, and 205 out of 1580 is 0.1297. Should be a 9. So which type of vehicle owner was more likely? Well, it's the owner type, or the vehicle owner which has the highest probability, which is the first case here. So therefore, EVs owners are more likely to have a home solar system. So part 3, there were 22,144 home solar systems installed in NZ by the end of 2018. Use the results from the survey to estimate how many of the home solar system owners in New Zealand also have EVs. So what's this? This is the probability that you can reword this to say, look, if you are a home solar system owner, what's the probability that you have an EV? So if you're a home solar system owner, what's the probability that you have an EV, right? Well, really, what we're saying here is this is the probability of having an EV and HSS as well. So what's this? The probability of HSS. So if we look at our table here, so what's the HSS? So which is it, a column or a row? It is a column, right? So we're looking down here. Now, what's the probability of having an EV from this column? It's 104 out of 354. So what we're doing is 104 over 354, and we're going to get this probability, which is 0.294. Now we need to multiply this by the 22,144. So that will give us the total amount of solar system owners in New Zealand who also have EVs. So 0.294, which is equal to, multiplied by 22,144, which is equal to 6505.58. I'm going to say we can't have 0.58 of a person, so let's get rid of that and round down. So we're saying 6505 is our answer. Part IV, give at least one statistical reason why using table 1 in your answer may not lead to a valid estimate in this case. Well, one reason is that the survey was done in North America. We are generalizing to New Zealand. There are many, cultural and let's say maybe systematic differences between countries, and we'll say risky thing to do. All right, moving on. So a similar survey was conducted in Europe at the same time. So we need to fill out the table. So it's just like a puzzle, right? So to get this value in here, we're just going to subtract across the rows, right? So all the rows and all the columns must sum nicely, right? So 225 minus 162 gives us 63. 271 minus 63 minus 23 gives me 185 in here. 96 minus 23 gives me 73 in here. what else do we know? We know that 1200 minus 96 minus 225 gives me 879 in here. 879 minus 185 gives me 694 in here. And then 162 plus 73 plus 694 gives me 929 in here. All right. So what do we want to know? We want to find the probability that a randomly selected respondent whose vehicle was non-electric had a home solar system. So we can rewrite this and say, given that the vehicle was non-electric, what's the probability that they had a home solar system? So first of all, our condition is being non-electric, so we look for that row and we highlight it. Sorry, I don't know what that was about. Then we want to know the probability that they have a home solar system. This is just 185 out of 879. So 185 out of 879 is 0.210. Did we calculate that before? No. What did you get? 0.210. But that's for the North America survey. Anyway, so final part. A newspaper article says that in North America, EV owners are 3 times as likely to have a home solar system as non-electric vehicle owners, and in Europe, they are only 30% more likely to have a home solar system than non-electric vehicle owners. We want to test these hypotheses, I guess. So I'm going to go over this quite quickly. So what are we looking at here? EV owners are 3 times as likely to have a home solar system as non-electric owners. So what we're saying here is we want the probability that given that you are an EV owner, that you have a home solar system, and we want to compare that to the probability of having a home solar system if you have a non-electric car. So we'll say non. So how do we work this out? What's the probability of having a home solar system given that you have an EV? So given that you have an EV, we look at this row here. We look for home solar system. So we're looking at 104 over 275 all over. Now the condition is non-electric. So we look at this row. We look for home solar system, which is here. This is 205 divided by 1580. So if we calculate this ratio now, this is 104 over 275 divided by 205 over 1580, we get 2.915 times. So is this equal to 3? Not quite, right? So it's close to 3 times, but a little under, so a bit misleading, right? So that was for North America. What about for Europe? So we're looking at this table up here now. So they're only 30% more likely to have a home solar system than non-electric. So essentially what we're saying, in Europe, the probability of having a home solar system, given that you have an EV. Oh, so we're doing the exact same thing just for the other survey. So given non. So if we look here, what's the probability of having an EV and then home solar system? 63 out of 225 over 271 over 1200. Okay, so if we calculate this, this is 63 over 225 divided by 271 over 1200. Okay. That does not sound correct. 1.24. I calculated something wrong. No, EV owners are only 30% more likely to have a home solar system. So HSS given EV is 63 over 225. That looks good. And then 185. Oh, I've gone too fast. I calculated the wrong thing. So if we look at the non row here, it's 185 out of 879. So now if we calculate this, 63 over 225 divided by 185 divided by 879. No, I still calculated it wrong. 225 divided by 185 over 879. We get 1.33. That sounds more like it. So what this means is that we are EV owners on average that are 33% more likely to have a HSS compared to non-EV owners. So we say 33% more likely. I think the cutoff was 30%. So it's actually more than 30%. So maybe only is a bit misleading. But it's actually better, right? So I guess we say this is okay. But it is actually greater than 30%. Alright, I think that covers everything I wanted to cover today. I hope you guys enjoyed this video. And I'll see you in the next video about the normal distribution. Cheers.